spark formation in barred galaxies. So yeah. Thanks for the contribution. It's few of my words. As you can see, I'm going to galaxy and bar. So let's have an outline for the talk. I will be speaking about some basics of galaxy and their structures, spiral arms for spiral galaxies, and bars for bar galaxies. Then I will come to bar fraction, and we'll see what is CNN and how can that be used in this field. So galaxies are, as you all know, gravitationally bound large systems, and the constituents are stars. ISL means interstellar medium. Those are composed of gas, dust, and cosmic rays, and also magnetic field. This is a huge field of study. This magnetic field, cosmic rays are very interesting. Next is center of galaxies. Many galaxies are bearing in their center active galactic nuclei. As you know, it is called AGN, and many are there also except exceptional cases. Other is dark halo. This is known as dark matter halo also. It was recently discovered and observations are going but not yet detected. Dark matter those are non-baryonic matters. Baryonic matters are the matters, as you know, proton or those things, those interact with lights and we can detect them. But dark matters aren't like this. But their presence can be felt. Or from observation, the first one was the galactic rotation curve. I think, okay, let me introduce the galactic rotation curve for dark matter halos.
Use that board.
This one. From center of the galaxy, if we calculate the rotational velocities of stars, and r is the distance from center of galaxy, the rotation curve as expected should go like that. It should be increasing and increasing. At the center of the galaxy, it should be highest, and then as you are going away, it should it is going away from the center. The velocity should decrease, as in the sense at that time theoretically it should be going like somewhat saturating or something like this. But observation we found that this was going on increasing and increasing. So few models were built, and those are and one of the most famous was dark matter. I don't think any others. So the stars interacting with dark matters, and dark matter can interact gravitationally, due to which the stars could maintain those higher velocities, not decreasing the velocities like this. Next, some basic models to describe the galactic disk. Okay, let me introduce disk. If we can see a galaxy, not irregular galaxy, there is a disk, some kind of disk is there. I think you can fit. Yeah. We'll also show some picture. So this disk approximately follows exponential function for intensity or brightness. So here R0 is some scaling factor, and I0 is also a scaling factor, and with that R is the distance from the center of the galaxy. And I am saying that this is just a simple and simplest model. This doesn't hold for all, or in practical it cannot hold for many. But while modeling a galaxy, we could use that. And similarly for density of stars, this also falls exponentially. Those are scaling factors, etc. And let's go to classification of galaxy. This is Hubble classification, Edwin Hubble's classification, and everyone know Hubble, I guess. Hubble's classification was based on the morphology of galaxies. It was one of its first kind to bring such classification. We can see this is kind of bifurcation. In this arm of the bifurcation, we have elliptical galaxies. E for ellipse, S for spiral, SB for spiral cup. And the numbers here suggest their ellipticity, or those numbers are eccentricity into 10. Suppose it looks circular. For a circle, the eccentricity is 0. 0 cross 10 is 0. For that, it should be 0.3. For that, 0.5 and so on. And this is S naught, and from that it bifurcates in two ways. One is SB and other is one is SB and the other is S. Bar, you can see the bar-like structure there, and those are without bars. We will come to bars more next. And those subtypes are based on the windings of those spiral arms. And let's come to spiral arms. We have seen there some basic types of spiral arms there, and it was really not understood how the spiral arms are forming or what are they actually. The evolution of spiral arms formation is yet not fully understood, but one of the famous hypotheses proposed by Cecilin and Frank Shu, it was in 1964. That was a mathematical model. Their hypothesis was that those structures are stationary density waves. That is, the spiral arms are there, and those have some specific angular frequency, and those are being as stationary waves. In the disk of the galaxy, those are standing as stationary waves. These are moving, but as a stationary wave, and in those arms, the stars are also moving with their speeds, and as I showed, speed also varies with distance from galactic center. Now, let's come to Earth. This is a spiral galaxy. It is NGC 1300. The middle part of the galaxy is the bar. So bars are generally some structures. As you can see, those are rod or bar-like structure embedded in the center of the galactic disk. And as you can see that those are in the middle of the galaxy, those have a large contribution in their mass, luminosity of the inner region, and also for the whole galactic dynamics. It affects the evolution and also kinematics, dynamics, all those stars of the galaxy. And components of galaxy, there are stars in the middle of the bars, many galaxies. There are AGNs, and others are dust and stars, right? As I mentioned. And those stars are orbiting. This is the bar, and thus those stars are orbiting around the bar-like structure, and the bar comes to. Okay, I'll come to that part more. And for observation, gas are mostly observed in radio spectrum. For that, radio astronomy is used. So gas bars or stellar bars, those terms are also used for different spectra for different purposes. Yeah, and the last one is just talking about the stuff I mentioned. Bars are in the bar, the stars are moving around the bar galaxy, and bars are really interesting. In a large galaxy, when you see bars, so we can easily feel that has a huge contribution and effect in the whole galaxy's evolution, formation, and I mentioned it earlier, mechanics and dynamics. In the bars, we can see young stars and H2. H2 is a term referred to ionized hydrogen regions, and those regions are mainly meant for star formation. So bars can be studied for star formation also. In many galaxies, you will find that the inner region of the bar are a huge place for star formation, and those star formation is mainly driven by one of the reason due to bar, which is driven by bar potential. As the bar is there, so the gravitational potential, some kind of gravitational potential wave will be formed there, okay, and which will driving gas from nearby regions to the center and other parts of that bar, and which will, as a consequence, drive the star formation. And now we also study bar fraction and evolution. Why do we study bar fraction? Studying bar fraction at different redshifts. Redshift, I guess you know, right? One of the concept is universe is expanding, so the light that are coming, the lights are being redshifted. But the concept I am saying that we denote redshift with Z. And we denote redshift with Z. Then Z equal to 0 refers to our home position. Means at this point we have 0 redshift. And as you are going further and further, the redshift is increasing. And studying bar fraction at different redshifts, with this we can see how the bar fraction was evolving with cosmic time. And why is that important? By saying bar fraction evolution in cosmic time, we can also infer how bars, or at what time bars started forming in galaxies, and what could be possible things that affected bar formation, and how bars are affecting galaxies evolution also. The term used for that is called secular evolution, that is slow kind of evolution. We refer to this as secular evolution. Bars also affect secular evolution of galaxies. So let me go to bars. So most of the case is that huge and more stable galaxies are with bars. It happens that we have seen in the evolution of galaxies, in many galaxies, as the galaxy is maturing over time, it is getting bar, because the stability is attained by transferring angular momentum from the outer region of the bar, that is, and the rearranging of matter. I can discuss pattern speed and impact of dark matter. Pattern speed is the speed at which the bar is rotating. The pattern of the bar-like pattern also rotates in the galaxy, and this is pattern speed. The pattern speed can be measured by different observations. One of the famous kind is TW something was there. I forgot the name, but that is not here in some kind of important thing. It was observed that the pattern speed of path were less than as we could expect, and the possible explanation was the presence of dark matter. Again here, while explaining the decrease in pattern speed of paths, we can explain with dark matter and the presence of dark halo. And strong and weak bars. In the galaxies, in some galaxies the bars look prominent and visibly those look clear enough to be distinguished as bars. Those are strong bars, and those have more impact on star formation and those stars. And the other kind is weak bars. Those are not that prominently visible, but some kind of structure can be felt that is there in the middle. And I can come to bar formation. To study bar formation, people used some kind of simulations. N-body simulations is being used from last 3 or 4 decades to understand the system of galaxy, how the bars could be formed there. And in many cases, it was seen that bars form spontaneously in the galactic disks. It was, I am again saying that observed from N-body simulation. And another thing was noticed that the bars could be slowed down. I mean, the formation of the bar that was slowed down by 2 things. One is the halo mass fraction. Halo is the dark halo mass fraction within the disk radius. While the bar was formed due to the gravitational interaction with the halo mass, the bar's formation was, the pace of the bar formation was reduced. And another stuff was heating up the disk. Heating up means the increase in random motion of gas and stars within the galaxy. That stuff could also decrease the pace of bar formation. And more interestingly, this particular thing is being studied recently also, and the consequences or main reasons aren't fully clear. The dark halo and its role in bar formation is quite complex here, and the final bars that can be seen in galaxies, those are considerably stronger cases where it grows slower. It means that in a case where the galaxy is already dynamically cold, means the randomness of motion of its components are less. The bars are evolving slowly, and those happens to be stronger and to last more. And cold, by cold I mean that the randomness of motion is less. In cold, most of the cases we say that the galaxies are disk dominated, the bars form within a year or so. But while if the galaxy is sufficiently hot, I am again making the point, randomness of motion is more. In that case, the halos can stay unburned, means the formation of bar takes more time. And this is a very interesting part of a galaxy which is yet not fully understood yet. And people are working a lot on simulations and also observations. And now I can come to the bar fraction relation with redshift. So this is our present time, and as you can see, the bar fraction is decreasing with the as the redshift is increasing. Redshift is increasing, that means that we are going further away in distance and also in cosmic time. The places there, 0.8, means we are seeing almost 4 billion years earlier. Or if you go 1, those would be even earlier. You can say 6 or 7 billion years. So the bar fraction at that time we can see that is less. And why are there less samples? Because while we are observing, we are at the center, and as the universe is, and as the distance of the universe is increasing, the more galaxies could be seen. But the pattern here we find about bar fraction is that bar fraction is increasing with cosmic time. So can we conclude that as galaxies are evolving, the bars are forming in the galaxies with the increasing number? So that could also support the theory or hypothesis that we previously mentioned, that as a galaxy grows to mature, it grows bar in itself. And N-body simulation showed that it was happening by itself. But yet the proper mechanism of bar formation is not clear. Here I can show that this is taken from a paper mentioned here, and total bar fraction is there, and at that part there is strong bar fraction. So, okay. As I mentioned earlier, that in bars there could be strong bars or weak bars. So it is clear that strong bar, total bar fraction is always more than strong bar fraction. But the trend is similar for both cases. At earlier time, the bar fraction was less, and it is growing more and more. Yeah, bar fraction also from the observations it was found that it also depends on mass and luminosity. More massive, more luminous systems means the galaxies are bar. It was seen that there was very little evolution of bar fraction in those systems. I mean, those are already bar. The massive ones are already bar. So the evolution of fraction was less. And as I mentioned earlier, galaxies more massive, dynamically cold. I mentioned about this, dynamically cold, and rotationally supported galaxies. Those have bars. Rotationally supported means it's considered a disk and it is rotating, and in the middle there's a bar. It also supports the rotation of the galaxy. So there could be many things to be considered that lets us think that bars can help giving stability to our galaxy in many sense. Yeah, as I mentioned, the high bar fraction indicates that most massive systems are already mature enough and rotationally supported to host bars. This actually means that the conclusion from this is that massive and luminous galaxies are mostly bar, and those give their maturity. So I guess, or the community can conclude that as the galaxy evolves to maturity, it gains bar, or it tends to gain bar. And this is not a part of astrophysics. I can just briefly say that this part can be used for calculating bar fraction, as there's a paper by Shiva Abraham. She found a process of finding bar fraction using CNN. CNN is Convolutional Neural Network. This is a part of computer science, and in the last decade, object detection and object classification was very much introduced in every field, and in astronomy also people are using this. Object classification means that in bar context we have a barred galaxy or we have an unbarred galaxy. So just using some algorithms, I mean we can make a model. I'll take 5 minutes. So just let me give a very introductory part of it. This is a part of machine learning, and which is growing its popularity day by day in different fields, including astrophysics. So the basic funda of machine learning is taking some already existing data where we know galaxies are barred and unbarred, and we will train them making with some models, and those models are some CNN models. Those different kinds of model exist. And we train means we have a model, means we have a machine. We are telling the machine that look, this is barred galaxy, this is unbarred galaxy, and there are many sets of such images. Galaxies, these are barred, these are unbarred. So the models are trained like that. The model can look and get trained to know which is barred, which is unbarred. It is called supervised learning in machine learning. And after that, the model is almost ready to tell me which is barred or unbarred. Then we use testing. Why do we use testing? To verify how much our model is doing good. Because it is machine, that can't say properly that this is always a barred galaxy. There's always some error in the model's prediction. So we will try to improve that with different algorithms. There are so many stuffs there. And after that, testing is done. In her paper, what she did was taking data from SDSS. SDSS sloan deep sky survey for different. She took data of. Okay, she used the data to train the model, and after that, it could be the model is ready, and after that I can have huge sets of galaxies, these huge sets of images, using which I can use the model to tell which is barred and which is unbarred. There will be some mistake of the model, but it will be up to some errors. But if the model goes good, we can use that for huge number of galaxies, and using that we can find bar fraction as barred galaxies by total plus NU. But these are later stuff. In this place, making the model, training this takes huge data, and also improving the model. This is the main challenge of such CNN based object classification, and this can be used but it is a still growing field. Here. Okay, this is done. This was all. I just wanted to just give a brief of this here and how can this be used in many science fields, including finding perfection. And I tried to include some basics of stars, galaxies, how those could evolve, and this field here needs to know so many stuffs. And references, some of the references, I might miss few. Thank you.